In this screencast, I want to talk a little bit about moving from an acceleration versus time graph to a velocity versus time graph, and then to a position versus time graph. The question says a runner starts at rest and moves along a straight track. Her acceleration versus time graph is shown. Draw the position versus time and velocity versus time graphs. So let's come down and look at here. We have the acceleration versus time graph. Remember, when we're moving from the acceleration versus time graph to the velocity versus time graph, we want to take the area under the curve. So from t equals 0 to t equals 1, the acceleration is 0. That means that the change in velocity, delta v, is going to be the area under this curve. Well, the area here is just going to be the acceleration times delta t. And from 0 to 1, that's just going to be 0. There's no area under this graph. And so the velocity is going to remain constant. So we have to think about this. If I had said the runner started at 5 meters per second and her velocity was constant, we would start up here at her initial velocity. So I have to go back to the problem statement and read it again. It says that she starts at rest. So that tells me that her initial velocity is 0. And the slope of this line should be 0. It should be flat because my acceleration is 0. So the slope of my velocity versus time graph is equal to my acceleration. Now I'm moving on to the next part of this graph. And so the acceleration jumps up to 4 meters per second. And I can look at the area under this curve. And that's going to give me my change in velocity. So here I have my velocity. My change in velocity is going to be equal to 4 meters per second squared times, and I'm going for 3 seconds. So I should end up at 12 meters per second. So I should go from this point here at 0 up to, my change is, now I'm at 12 meters per second. 12 meters per second. And that's just going to be a straight line. If I looked at the slope of this line, the slope of this line should be equal to my acceleration. So for every 1 second I go up, my velocity should increase by 4 meters per second. So from 0 to 1, I went 1 second and I increased by 4 meters per second. And then from 2 to 3, I increased by another 4 meters per second up to 8. And then from 3 to 4, I increased another 4 meters per second. So for every second, I go up 4 meters per second. So this is what my graph looks like. All right, now I have another flat line. So I have this section here has no area underneath it, 0 acceleration. So my velocity, my change in velocity is going to be 0 meters per second. So that's my change in velocity. That tells me that my velocity remains constant. My final minus initial is 0. My initial was 12 meters per second. My final should be 12 meters per second. So I have my change in velocity. And then I can finish this off with this last section of the graph. Now this is kind of tricky because it has negative area, because the line is underneath the x-axis. And so here my acceleration is -3 meters per second squared. And so my change in velocity, delta v, is going to be -3 meters per second squared. And I'm going for 4 seconds here, from 6 to 10. So times 4 seconds. And that's going to be -12. -12 is going to be my change in velocity. -12 meters per second is my change in velocity. Oh, sorry, I just realized you couldn't see that fully on the video. So we're looking at this area down here is -3. So here I go from, I started my initial, this is my change in v, delta v is equal to -12, and that's equal to v final minus v initial. My initial velocity was 12, and so my final velocity is going to be 12 minus 12, or 0. So I'm going to go from this point back down to 0 over here. And again, the slope of this line, for every second I go, so if I go from this to here, every second I go, I should lose 3 meters per second for every second I move over. And so my acceleration here was a little bit less than magnitude. Here I had an acceleration of 4, and so this is a steeper velocity versus time, and then this acceleration was -3. It's a little bit shallower. But now I have my velocity versus time graph. Moving from the velocity versus time graph to the position versus time graph is the exact same thing. I'm going to want to take the area under the velocity versus time graph, and I have to think about where I start. So where I start matters. In this case, I am not given, in my problem statement, I'm not given any point where I start. So a good assumption then is that I'll just call the point I start at x equals 0. So here's for the first second, there's no area under my velocity versus time. She must have been sleeping when the race started, because she spent a whole second not moving. And so her position is not going to be changing. The area under that red line is going to be 0. And so her change in position for the first second isn't going to matter. Now we get to the velocity versus time. So anytime I have a constant acceleration, I'm going to see a parabola in my velocity versus time graph, or my position versus time graph. So I need to think about what my slope should look like. Well, here my velocity right at the start is 0. So my slope should start out as 0. And my velocity is getting bigger, so my slope should be curving bigger. I should see a shape that kind of looks like that would be what I'm looking for. But it's also helpful for me to calculate some actual values. So if I try to calculate this, the area under this green part of the graph, that's a triangle, and so the area under that is going to be equal to my change in position, the total change in position from 1 second to 4 seconds. And so the area of a triangle is going to be 1/2 base. In this case, the base is my change in time, which is 3 seconds, times my height, which is 12 meters per second. And so I could calculate that out. That's going to be 18 meters. So my change in my delta x is going to be 18 meters. So I'm going to start at 0. I'm going to end up here at 18 meters, and I said my graph should be kind of curved like this. My next area that I have is this area under this blue graph, and this is a constant velocity, so this should remain a constant slope. The velocity at this point right next to this line and this point here should be the same, and so I should be going from I'm going to be going, this area is going to be 2 seconds times 12 meters per second. I'm going to increase another 24 meters. So I started 18 meters. So 18 plus 24 is going to be 42. So now I see I have a problem. I ended up way off my graph. So I continue straight all the way up to 42. So this would be at 42 meters. Now, because the initial position wasn't given in the problem, I assume the initial position was x equals 0. It wouldn't be wrong if I had drawn the graph, if I'd started down here at like -20 meters per second, or sorry, -20 meters, it wouldn't be wrong for me to draw this line like this, where I end, now I should be ending at 22 meters. That would be a fine graph for me to draw. But I'm going to stick with my initial assumption. So this would say the initial position was -20 meters, and then all of these delta x's, I went from -20 to -2. My delta x was 18, and then my second delta x was 24, so I went from -2 up to 22 meters. That would be fine, but I'm going to keep it how I started, just so you don't have to, if you're taking notes on this video, you don't have to erase your work and keep and start over. So the last thing we have is we have this, now we have a decreasing velocity. So we have this purple area with the velocity. The velocity is still positive, so my slope should still be positive, but my acceleration is negative. One thing that a little trick I like to use is if my acceleration is positive, so down here my acceleration was positive 4. If my acceleration is positive, I draw it like this, the concavity of my position versus time graph should be concave up. And if my acceleration is negative, the concavity of my position versus time graph should be concave down. So I see here that this shape matches that smiley face for the positive acceleration. That's a good sanity check. And this second part of my graph has negative acceleration, so it should be concave down. It should taper off like that. And so we know also that at t equals 10 seconds, the slope of my acceleration graph should be 0. And at t equals 6 seconds, the slope it has the same velocity, so the slope should match. So this should start with the same slope here, and it should level off at t equals 10 seconds. And it's going to be concave down. So we can guess that the acceleration versus time graph is going to look, or the position versus time graph is going to look something like that. Now, if we want to know where we end, our endpoint, we could take the area under this curve, and that's going to give us our delta x. And so, again, this shape is a triangle. I have 1/2 times my base, which is going to be, this is my base, it's 4 seconds, times my height is 12 meters per second. And you'll notice the units cancel out, and I'm left with what I'm looking for. The seconds cancel out, and I'm left with meters. So I have, I have that my delta x is equal to 24 meters. Or because I was at 42 meters, I should end up at 66 meters. And that's going to be my final position. So that's going to be my position versus time graph from that acceleration versus time graph. Thanks for watching. I'm going to post another video where I move the other way, where I move from position versus time towards acceleration.